live in Streamlabs, and
it says it's live.
It does say it's live. I'm just waiting to see if YouTube says it's live. YouTube
That's the important one.
Yeah, YouTube does say it's live. Hopefully everybody can hear us and see us, just as our internet connection goes to crap. But hi everyone, welcome to the Supercomputing 2023 wrap party. You're on the TechTechPotato channel, but we have an array of friends here to join us. So let me introduce you to everyone who's here. On my side, this side, because I can't point properly, that's Domenico. Domenico's been helping me with some recording and editing lately. So if you've seen a video recently from TechTechPotato, that'll be his stuff. Below me is Felix. Felix is well, we'll get to what he is in a minute because it's part of the topics of the show. But he specializes in reduced precision compute, and he joined the More Than More TechTechPotato team at Supercomputing as a writer. We flew him in from Canada. And then in the corner is George. George is the editor-in-chief and head honcho over at Chips and Cheese. He was also at Supercomputing 23, and the four of us pounded the floor for the best stories we could see and lots of different silicon. Let me bring up this, and this won't work because I only have 2 monitors and not 16. Let me share my screen because let's see if this works. So if you are a fan of the Chips and Cheese, and you should, go over to chipsandcheese.com and you can see fun articles. I always like to say, like what we used to write at Nantech, and I'm not sure if George likes that comparison. Go on, George.
Yeah, no, it's an honor to be compared to what you used to do.
It's a handy comparison for people who don't know what it is. Yeah. These are the guys who reviewed Pentium 4 20 years after it was announced. So I always
the technology is interesting again. It's a good, interesting look at the technology.
A few decades removed, no problem.
No risk of breaking embargo.
George is also half of the team that gave a very nice AVX10 explainer at Hot Chips.
Oh yeah, yes. George has appeared in a few videos. Felix is going to appear in some videos soon here. We just need to find time to record it. And then obviously, if you want to go read some of my stuff, you obviously have the videos. We do have articles as well. Latest one, interview with Dr. Anne Kelleher. That was really fun. But we've also got the articles here that we've got from Supercomputing. We'll go into some of these a bit later. Okay, so again, thank you all for coming. We do have a dog in the background. we do have a list of things to talk about. If there's stuff that you want us to talk about, please do shove it into the chat, and we'll get to it. But first of all, we have to say to all of our American viewers, happy Thanksgiving. I do appreciate that this is important time for you all, friends and family. And if you're watching us, then that speaks more to your friends and family, I believe, than it does to us.
What does that say of my friends and family?
You've got cranberry sauce on the go. And we had an argument about what's the best cranberry sauce earlier. Well, no, we didn't have an argument. I was being facetious and I said tinned.
Yeah, no.
Yeah. So Thanksgiving, for the rest of us, for Dom, me, and Felix, it's just a regular Thursday with slightly fewer emails. But one thing to start off with, though, is I appreciate most of the audience may not have met Felix before. I've known Felix for a couple of years through the HPC scene, and we have to celebrate today because Felix has a job. Woo!
I'm employable. It's officially employable. Can change that.
Employable.
Take that box off the old resume.
Felix accepted a job 6 months ago, and
29 weeks on Tuesday.
How old's your first
Not
one?
that I'm counting.
6 months, 29 weeks. Yeah, so he's been waiting for the slow machinations of government to go through, and it seemed as of this morning they have.
Yeah,
So
super exciting role.
So after he's done the videos here with me about supercomputing, he's done. He can't ever write anymore. Yeah.
No hot takes on
it's,
Twitter or Mastodon anymore.
Well, it's government.
Mastodon's fine. Who's going to read it?
Yeah,
True.
True.
Actually, no. The people who Felix is working for probably reads Mastodon.
Yeah.
Threads, or Trump Social. You're fine. You can post there. That'd be fun for you. So, supercomputing 2023. I have to get this photo up. I have to add this because this is where we were. This is the photo that we took on the day. And this was actually George's birthday. So happy birthday, George. We're all celebrating.
Which I didn't find out until the day after, by the way. No one had told me.
I told you. I told you.
Oh.
Also,
honestly,
really
the whole thing is a flash. Truth be told, all
yeah,
of SP
yeah, that's like Patrick was like, I forgot. Like, yeah, Patrick was like, I forgot. I'm like, fair enough. Like,
so this is Patrick Kennedy from Serve the Home, which I hope you all know and love. I see this guy more than I see most of my own family, just because we end up at so many events together. And behind the display is actually a number of attendees. Felix's face is in the way. Record for Supercomputing 2023, over 14,000 attendees. I think last year was something around 8,000, as in they had a good turnout, but not a great turnout because people were unsure with the pandemic and that. I mean, by that time, I was already traveling for events, but I ended up at an event in Maui, and that took precedent over Dallas. I think it was in Dallas. But this year I said, if you have that Maui event at the same time as supercomputing, I'm going to go to supercomputing. So and to be honest, the show floor, especially the first day, was manic. Yeah. It's Dom and I had we had some sponsorship obligations we had to fulfill. And we thought, let's go on the show floor at 10 a.m. and start recording those videos because that'll be the quietest. That when people slowly walk in. No.
Hindsight is 2020. And it definitely kicked our asses that first day.
I think I decided to go back. After recording those videos and seeing that they're all rubbish, I went back to my room, had an hour to myself, had something to eat, and then came back, and the rest of the day was fine.
Me and George were actually in a separate hotel so me and Felix were in a separate hotel to George and Ian. We could hear Ian screaming into his pillow from ours. It wasn't
across the city.
Yeah. And considering that you guys could hear it, it was very loud in my room.
Honestly, noise canceling headphones didn't put a dent in it.
Yeah,
it's George and I booked all the way back in June. And then Dom and Felix coming was sort of like a last month thing. Ability to get them both out there, thankfully. But yeah, we've got a bunch of pictures in this deck to show you. So let's bring up the first topic, and let's see if I can find the picture here. Everybody gets a preview because I didn't order these. RS.
For people wondering, we decided to do this about an hour ago.
That's fine. It's fine. So let's talk about what supercomputing is usually about, and that's the top 500 list. Top 500 is the official curated list of the fastest supercomputers in the world, but only those who actually submit results get to go on it. So you'll see a lack of Chinese supercomputers because they don't deem it worthwhile to submit. Actually, I'll bring this up because Greyhawk Jaws asks, if you're sponsored, can you get an exhibitor pass and get in at 8 a.m.? Yes, that's what we ended up doing.
You were 2 seconds faster than me.
I've never done. I never had sponsorship obligations at an event before, at least none that were directed and dependent on that, especially not filmed. So, but I mean, it helped pay for a couple of these guys to come to the show. So, But okay, so top 500. Let's get back. No Chinese systems. We think Chinese systems have come quite high. Number one this time around is Frontier, but Aurora, the system we all believed should have been number one, it didn't.
Yeah.
Which is there's a good side and a bad side. Who wants to take the good side? Who wants to take the bad side?
Felix.
Felix.
Yeah.
Go for the good side.
The good news
I know
is,
you have...
So I want to be fair. I'm wearing the Intel scarf partially out of like a thanks to some friends at ALCF and some friends at Intel who I know have put in a lot of long hours and burn a lot of midnight oil to get Sapphire Rapids delivered, to get Ponte Vecchio delivered, and now with the Aurora supercomputer getting Aurora at least partially operational and able to finally do science, right? The goal of these big systems is they're a tool to actually get the science done beyond the whole glory, the prestige of being the number one or the number two or the number 10 in the world. What's the goal? The goal is get some science done. And the good news is Aurora, at least partially, is starting to get science done. It's 5 years later than it should have been. And it's been through many iterations to get there. But people are finally getting to run code. They're finally running submissions. There's a prize in the supercomputing world known as the Gordon Bell, which you can sort of compare to, say, like a Nobel in this specific area. And two of those that were finalists were based on work done on the Aurora supercomputer. Now, the kind of news around Aurora is that it's supposed to be a 2 exaflop machine. So if you think of your normal GPUs, those are best case scenario measured in teraflops. So we're talking teraflop to petaflop and then petaflop all the way to exaflop. So these are huge, massive machines. And the kind of news about Aurora is that it was supposed to be over 2 exaflops. Now, as you can sort of see on the edge of the table on screen right now, unfortunately, it came in using only half the machine was at 585 petaflops, which is still huge, massive number. But that's less than half of the machine. That's half the machine, and it's performing less than half as well as you'd expect. So scaling is far from ideal here. And there's some concerns in that it did that while drawing a lot of power, namely 24.7 megawatts, which is, you're drawing more power than the number one in the world and getting less than half the performance. So you scale that out and you look at what if we had the full machine of Frontier down at Oak Ridge. If we had that full machine going, we still wouldn't be beating them using over twice the power. So it's not a good news story for Intel.
Yeah, so we covered this on our article that you can read at more-more.com. But we asked in the press briefing, which is actually a pretty good press briefing, at least when we got to these numbers. And we asked, that power number seems high because, again, if you scale to 2 exaflop, this would be 100 megawatts. But we know the facility can only do 60, really. That's what it's been advertised as doing most. And they said, chances are the rest of the system was on, but either may have been idle or may have been running other code. Somebody else's workload may have been running on it. So they confirmed that it was a half system run. So realistically, we should be at the 1 exaflop, 1.1, 1.2 exaflop, which should have been number one, almost pretty much for half the system. But it's not. So the fact that they're only extracting half performance, I mean, usually these systems from you order them and then the contract gets renewed and renewed and renewed. Then they get delivered with the different hardware than the original contract had. And then it's essentially a stage of install and bring up. With Aurora, Intel and HPE supplied compute blades, but with the regular Sapphire Rapid CPUs and then Ponte Vecchio or GPU Max. And then over time, they've been updating it to these Sapphire Rapids with HBM CPU Max editions. The last 25% of that replacement, I believe, was meant to have finished in August, early September. And at that point, you do what's called a system bring up. So this is, you run various amount of codes, you make sure everything's working. A system this big, now for for argument's sake, say you have one piece of failure, one hardware failure. You got a 1 in 1,500 chance of it happening on a day. So once everything's meant to fail once in 5 years. If you take that as rote, this system's meant to have 20 failures a day. That's hard if you have code that runs for months. You have to have resilient code that deals with hardware failover. So bring up is difficult with systems this size, and especially with a workload that they use to measure for the top 500. So in terms of performance, we think there's still a lot of optimization to be done. George, you've actually tested Ponte Vecchio. How was that for you?
So speaking of optimization, I suspect that Aurora's code is going to have to be, in our experience, Ponte Vecchio was the most finicky GPU. It needed a lot of tuning. We had to go back and forth on Intel for specific tuning for our article, and even then it wasn't ideal. So I expect there to be a lot of optimizations, and that simply comes from sort of the architecture of it. It's very much Intel's first, not HPC product, because they had Xeon Phi well beforehand, but sort of their first huge SIMD machine, so to speak, even though Phi was still a huge SIMD machine. This is even bigger and more complex.
To be honest, I remember Phi bring-ups taking a little bit of tuning as well, and they had high-performance groups to do that. I mean, the modern version of Phi is Sapphire Rapids with HBM, and there are some systems in this list that do amazingly well in terms of optimized performance. So architecture here is different and doesn't sit on the 2 decades of NVIDIA optimization that are available. So it's we do have to wait, obviously, to the next run of the top 500, which is going to be in March, even though it's called June. May. It'll be in May, because they're putting it at ISCs in May again, where they do this. But speaking to people at Intel, there was, I think, quite a hope that they would, still perform highly. I mean, second's nothing to sniff at, as Felix said. Science is getting done, and as I wrote in the bottom, people are still alive. Just because Portal is Portal.
Casual Portal reference. Always worth doing. And
so we have to wait and see. The thing is, they've promised it to be number one, or at least the expectation. Perhaps the promise is the wrong word. The expectation is it would be number one overall. But coming right up ahead is El Capitan, which is new system. AMD has said that all the revenue for that system is going to be in their Q4 financials, which is a few weeks away. So that system must be being shipped to Lawrence Livermore soon.
If Lawrence Livermore is paying, then that means that it's basically delivered and done, and probably even turned on at this point to some degree.
Or at least parts of it are turned on.
Yeah.
So the early science part of it, which is normally like 1 or 2 racks, that's already on and being integrated. Their new really advanced storage system and their new software distribution system for running on tens of thousands of nodes, that's already operational. The question is, will the full machine bring up be done in time to actually submit a run to ISC come early next year, right?
So
that's also. Oh, go ahead.
So as someone that hasn't paid attention to most of this, I'm kind of getting into it now. El Capitan, is that an update to Frontier? So it's like an all AMD system, or
it's a brand new system,
separate system.
Okay.
But it's using customized AMD Milan, so the I/O die is changed to support the next generation Infinity Fabric, and then it's using MI300As.
Okay.
And El Capitan is just MI300As as far as I know.
Yes.
The Max Planck SC is using MI300A and Genoa, I believe.
Right.
And then
It's
there's
my understanding
and then
that El
there's
Capitan is a pure MI300 system.
yeah, and then there's
You
the
won't have
other MI300 system also at Lawrence Livermore called Tulamine, which is essentially the public version of El Capitan.
Yeah, it's El Capitan's going to be spun up. They're going to run some test codes on it, and then it's going purely for government.
Yeah, so El Capitan and largely Lawrence Livermore National Laboratory, they're not Department of Energy labs in the United States. They're what's known as NNSA, I believe, National Nuclear Safety Administration laboratories.
Right.
So the idea there is that they worry about, say, the nuclear stockpile and those types of, shall we say, more private codes that the U.S. government needs.
Yeah, Oak Ridge is where I do about nuclear stuff, so that makes a lot of sense.
So you'll have about 10% of that system, which will be available for public science like other machines, whereas the remaining 90 or so % will be moved to classified work, shall we say.
So slight correction, Tulamine is actually its own machine as far as I know. It's not a segmented part of LCAP.
Yeah. And to Alan's point that we've put on the screen, didn't we hear the same complaints about the Frontier bring up? Because MI250X, I know that AMD's GPUs have also had a rough time in terms of optimization. Speaking with hearing the Lumi guys, Lumi is currently number 5 in the list. They had to rewrite the driver stack to get it to work. I've heard similar things from other companies using MI250X. The big thing about MI300 is that we still don't have all the details for it because the big launch for that chip is on December 6th. Hopefully there we're going to get more information about architecture, more information about what the benchmarks look like, and software support. I'll be there, George will be there, and I know PC World will be there as well. We'll get some more info and do some more content around specifically MI300A and X, which is kind of like the X is more the AI version. So
yeah, the kind of the way I've been explaining it to people has been, if you look at the name MI300A, treat the A as APU. So basically what's happened is that AMD has gone, APUs are a good thing for efficiency and performance and integration. What if we did one of those for supercomputers? Is the very short form version.
What I really want is I want an MI300A and a desktop computer. Like, just give me like a NUC with an MI300A in it, please. That would
MI300.
that would be great.
I'll take 12.
Yeah.
This is an image of the MI300A because there were actually a few on the supercomputing show floor. I don't think I have the one where I've got my gigabyte system and me doing I put it as a thumbnail to the video. That's why.
Yeah.
So Gigabyte had a system with 4 of these. So it looks like a quad socket. And up 24 Zen 4 cores. Zen 4 or Zen 4C? I keep forgetting.
Zen 4.
Zen 4,
I believe.
And then 3 lots of GPU chiplets. And then 128 gigs of memory. HBM3.
Yes.
I think it's 192.
It's 192 on the X version, 128 on the A version. Yep. Why the difference? I'm not positive. I suspect it's because of memory vendor timings. Like AMD sort of had to get MI300A out, and then it
might be an HBM3 versus 3E thing.
We're not sure because of some funny calculation that AMD did with MI300X. They sort of like knocked down what they said their memory bandwidth was. It was weird. There was a 0.9 times factor if you go look at the endnotes. It was odd, and I was like, okay, sure, but
it could be something to do with unified memory architecture as well. Perhaps there's some limitations in how they're doing that there. Or memory controls. So this is the MI250X. This is currently in Frontier. And then we've got the MI300A. And then this is the MI300X, bad picture, but just to show off the size. It's about the size of my business card. the best I could do, because it was behind this perspex, behind the glass. It's really annoying when they do that.
Of it.
Yeah.
To be honest, come December 6th, I think I'm going to be able to.
And apparently none of us were cool enough to hold it, unlike Patrick, who was cool enough to hold it.
Yeah, Patrick maybe gets all the access. So,
also, sort of, just quickly going back on the whole bringing up scenario, something that isn't talked about is networking. Networking on supercomputers is absolutely a bear. So that was also a lot of the issues with Frontier's bring up, and is likely part of Aurora's bring up issues. Just simply networking is such a bear on systems like this. And it's not necessarily hardware related, although we've heard some things about Slingshot. It's insane at this scale.
The one other thing to note from this top 10 list is that at number 4, we still have an ARM-based CPU-only system from Fugaku. But really, number 3 is the surprise.
Yes.
Number 3, nobody expected there to be a submission from a cloud provider about a supercomputer scale system with performance just shy of Aurora. The funny thing here is that we were told this system was installed, brought up with a benchmark run, and then handed off to the customer that acquired it in 3 days.
Yeah. Specifically, they finished it plugging everything in on Friday. The benchmarking and integration folks got 3 days to then do a submission for the top 500 over the weekend. Come Monday morning when office hours opened, the system was flipped onto a customer, and that system will never be seen again.
And as far as we know, that is not actually all of the system. That is
it's not
some percentage of the system in question.
Now, imagine if they had time to optimize it.
Well, that or just use a little bit more of the hardware there, and they could have probably dethroned Aurora.
Looking at how close they got.
We spoke to a person who was in charge of it, and he said it could have been 3% either way. They could have turned on another rack, and that would have been it.
It would have been number 2, unquestioned.
Yeah, right? But it's cloud. It's a fraction of a system, and they're using a known hardware, software deployment that works. So the only thing they didn't submit, which I found really annoying, was power. However, we were told that they actually did this run like 4 months ago, 4 or 5 months ago, whereas Aurora was done last minute. They're still going back through the logs to submit a power number because
they're going to try.
They to be honest, I think they could just put a power meter in the wall and see what's running on it. What's running on that fraction now, and then just take that as a number.
Yeah, because the people we were fortunate enough to speak to, it's not that they don't collect the power metrics in Azure. It's just that's in a log file some way, and that's not the sort of thing that normally you keep for long-term retention.
Yeah. Though, to be honest, for a supercomputing submission, you should submit it. Number 9 doesn't have a power as well, even though it's simply a SuperPod system from Nvidia, the Nvidia DGX. And we spoke to one of the guys who are involved in this whole top 500, green 500 thing, and it sounded like power numbers aren't necessarily aren't a requirement for a submission anymore. That makes me worried that we won't get power numbers in future. And this is an example of that. However, there seems to be enough people in the community who want to see the data and some honesty that we might get it moving forward. If you go to the article on this and you have a subscription, Felix and I go into where some of the newer systems are coming from, but also some of the power efficiency numbers, RMax to RPeak, or RPeak to RMax. I always get them the wrong way around. about just how efficient some of these architectures are for doing this sort of workload. Then there's the other argument that this workload isn't representative of HPC codes. So there we go.
Yeah.
So yeah, aside from that, we've gone through the MI300A. Again, still excited for the December 6th event. It's what do you guys want to see at that event?
I know what this man is going to say, and it starts with an R.
And more, well, what I want to see more ROCm support for one. That's been the kind of Achilles heel of a lot of AMD's stack, both consumer and HPC focused, has been great hardware, but they've been under investing in their software teams for decades, and it's really caught up with them, where you just can't, for the longest time, you couldn't trust. And in a lot of ways, you still can't trust the software to actually deliver on what the hardware is incapable of.
This is going to support ROCm. You can bet your bottom dollar. But my main argument to that is AMD has 10 times fewer software engineers than Nvidia or Intel. One, because the company size is a factor 10 smaller than Intel. AMD and Nvidia are about the same size, but AMD's product portfolio is so wide by comparison. So, but given what Lisa has said in the last year, ROCm is moving up to being a first-class citizen. We just need the launch of, say, things like ROCm version 6. We need full support for HPC and machine learning workloads, and I think George wants to say support for consumer cards.
Well, not just consumer cards, but like if AMD could somehow just flip a switch and enable ROCm not just on consumer, and not just ROCm, but also all its associated libraries, like Omni-Open, on consumer GPUs, and more importantly for them, laptops, because that's a massive market that they could tap. Not necessarily for writing very performant code, but just writing code, period. Right? That's a massive market that they have. And I think that needs to happen. Like, it needed to happen yesterday, but it needs to happen now, essentially. And I think people really want an alternative. You saw a lot of people using Arc. However, Arc has its myriad of issues.
What are consumer cards? Intel's consumer.
Intel,
the Intel GPUs.
So they have their issues, and Intel's acknowledged that. But I think you really see that people want an alternative because a monopoly is good for no one but the monopolist. So
I remember seeing some news earlier this year, about June or so time, where AMD said they're hoping to A, bring ROCm to Windows, and B, bring it to RDNA 3 consumer GPUs.
So
I don't know if it's happened. I don't know if that's happened yet, but
so it has TM, kind of. It's complicated.
The 7900 family is supported.
Okay.
7900, 7600, 6900, and 6700. I'm not positive about that last one. However, those have HIP SDK support in Windows. However, not all the libraries work. Like Omni-Open don't work in Windows, and those cards don't actually work in Linux either. It's a mess. It's a mess.
The compatibility of CUDA.
Yeah.
So I've been working with.
Let's bring it back to MI300. We're way off topic.
I know. It's a live stream.
Yeah, it's a live stream. December 6th event. So speeds, feeds, official confirmation of quantization support.
Yeah, the other thing that I've been sort of poking and prodding some of the AMD engineers to do for MI300 is we have MI300A, the APU of MI300. We have MI300X, the GPU only thing. What I'm really interested in personally is a sort of MI300C for CPU only. Because you look at high performance computing codes, and there's a lot of those codes that, as much as we'd love to run those on GPUs, and they probably run quite well, you're just never going to get those codes ported over to GPUs, right?
Mm-hmm.
So there's a lot of areas, and this is actually why Sapphire Rapids CPU Max with HBM is a really interesting product, is that most of those codes are not compute bound, they're bound on memory bandwidth. An MI300C with tons and tons of memory bandwidth to throw at those codes would give you a huge speed up for those, say, research centers and universities and so on that can invest in hardware but don't necessarily have the budget to invest in creating entirely new positions within their departments of research software engineers that go and rewrite these codes for new applications, new hardwares, new accelerators. Going back a decade, and I'll make it a brief tangent, Ian. If you look back at AVX 512, a lot of the promise of AVX 512 on Xeon Phi was, hey, there's this new instruction set coming. You can write it and do some special things for the Xeon Phi accelerators. But broadly speaking, your codes will be able to run on AVX 512 enabled CPUs, which is mostly true, right? So because at the end of the day, most codes run on CPUs, and sure, you can get more performance, but you don't necessarily have the resources to invest in that. So there's a lot of centers where even if they have, say, MI300A and they have this huge GPU portion on chip, that GPU portion is never going to get touched. And it's only going to be running on the CPU because that CPU will have HBM. And HBM is worth its weight in gold, right? And I think we're going to touch on it later on, but that was the big news out of Nvidia at Supercomputing, is that they have a new product in the form of the Hopper H200 GPU. And it's the same silicon as H100. And we'll go into the details later. But that got a memory upgrade. And then suddenly it's almost twice as fast across a lot of applications, purely because of a memory upgrade in slot.
Memory capacity or memory bandwidth?
Both.
Because depending on whether you're HPC or machine learning,
exactly,
it matters, right? So
huge.
It's
hugely important.
Yeah, I was going to say from the event, I also would like to see pricing.
Yes,
because we'd like to be able to put a stake in this in the ground. Power. They've already said roughly about 500. I think is it no. So Ponte Vecchio is about 550, 600. We're expecting this to be about similar. That being said, some of Supercomputing was talking about let's look at the next generation 1 kilowatt plus.
So actually, if you go and you look at AMD's endouts, MI300X is rated for at least up to 750 watts. MI300A is rated for up to 850 watts.
Doesn't beat Tachyon.
Oh boy, that's a can of worms there, Ian.
It's a lot of people. What this is doing is this is increasing the power density inside servers, and as a result, servers are going to need a lot more power. So this means we need something like, and I'll bring it up here just because I can. Who wants 85 kilowatts in a rack? We saw a company who now claims to cool 85 kilowatts in one rack. However, you need about 4 racks worth of space to do it.
Yeah.
It's not perfect, but it's a start.
We're running into the issues where you have so much hardware in a rack where you're having to double up on your concrete or your other support systems. Right underneath the floor, like we're truly back in the old mainframe era, where you had to have specific pylons reinforcing the rows in your data center where certain machines were going to be, because they will crack the concrete foundation. They are that heavy.
You have to do that with EUV machines already. They have to have speed built in special areas, and you have to have ceilings so high, and then you need to have support trusses around them and everything. So. more powerful chips doesn't necessarily solve any problems that we have about power consumption and floor space in modern data centers. However, it does mean more juice, more power, more everything.
More power.
It's that's going to haunt me, Felix. That image. But TSMC did publish papers last year about how to cool 2.6 kilowatts on a 700 square millimeter monolithic piece of silicon. One of the advantages of going to multi-die now is we are spreading some of that energy around. However, heat soak is still a thing, and more advanced cooling is coming. I think Alan said, somebody said earlier that one of the things they were impressed with at Supercomputing was just the variety of cooling options that people were showcasing. New air cooling setups, new liquid cooling setups, and we always get immersion cooling, but that never really takes off. But liquid cooling is becoming, essentially a staple. You need it in your data center these days. That being said, if you have a 5 kilowatt rack and that's all your colo can do, does it really need a kilowatt of liquid cooling? I don't know. So
this is kind of starting to be the discussion point in HPC, and a little bit in the AI space is the discussion of like power efficiency and power density, right? Because costs in those co-location facilities are extremely high, and especially for power. So the best place to put a data center these days is you want a data center somewhere in the middle of like Phoenix, or like somewhere in the middle of nowhere, where you have abundant solar power and abundant amounts of wind, right? And ideally, you then want to take these racks and put them 10, 20, 30 feet apart so that you don't have to worry about cooling density as much. But then you do that, you lose all your performance.
So Sam asks a question which is the opposite. How long until facilities are designed for humans to occupy that aren't designed for humans to go into so you can get more cubic feet per minute of air in?
Likely never, just because you're going to have people go and diagnose stuff.
Yeah,
like,
it's the reason why
I wouldn't count on that.
CPUs.
The reason why CPUs never might be a strong word, but I just don't see it, because sometimes you just need a human to go in there and be like, piece of hardware is broken.
I mean, like Microsoft has the submersible service.
Yeah, I know, but again, servicing them is a pain. As Davina says, we just moved to optical compute. That'll solve it all.
Well, actually, so that's an interesting point. Now that we're kind of discussing power and power density, on the show floor, talking to some of the optical folks doing, say, chiplet optical interconnects, or say chiplet style tiles out of optical. One of the problems they're running into is that if you have an actual optical die on top of your substrate, well, if you have a really high power piece of silicon right beside it in your substrate, you can actually end up warping the entire substrate because of heat density, and you have to correct for that mechanically.
So when Intel was first showcasing EMIB, the embedded multi-die interconnect bridge, they took several years. I mean, it's been in research since 2008, but they took several years to come out with a product that simply had 2 compute chips connected by EMIB because of that warpage, right? And the first one was the Stratix 10 GM X FPGA, and now they're more comfortable in doing it in things like Ponte Vecchio, and Sapphire Rapids. But it took a long time to get to a point where they were happy with the warpage. So it's a thing. But going on from power density and MI300A, one thing at the show that I was quite surprised to see were the Grace super chips up and running. Yes. So for let's see if I can bring up this slide. Let's just, there we go. So this is the Grace super chip, Grace. So 2 Grace chips, each has 72 ARM cores, 3 gigahertz plus, 500 watt TDP. Does it say how much memory is on it? Tons of memory.
It's so each
memory.
Grace chip has 480 gigabytes. So the super chip has 960 gigabytes of LPDDR5X.
And there's 900 gigabytes per second. chip-to-chip
Or
connectivity. I mean, I remember UPI 12.8. Yeah, yeah.
So
You're showing your age.
I'm gonna have to put a slight caveat on that 900 because really what it is it's 450 one way and 450 the other.
Okay.
So it's 900 combined if you're writing to both.
Yeah.
So
if you
at which
were
point you're going to run into other problems.
Yeah,
So
exactly.
if you were at the Supermicro
directions.
booth on day one, they had a Grace and Grace Hopper. And if you got close, you can actually kind of see the NVLink chip-to-chip interconnect in the not in the substrate, on the package itself. And it's minute. You have to be. I mean, I was taking photos of everything, so I got it. But it was actually really cool to like physically see the interconnect.
It's yeah. There were a few Grace systems on the show floor. We saw one at ARM running Stream, and that was showing 700 gigabytes per second memory bandwidth,
which is great.
So here, that was also low and unoptimized, and they didn't have a lid on the server, but they did have a perspex sheet on which sat on top of a monitor and a mouse. And then by the time we got there, because that was part of one of the videos we were filming, it had crashed. So, but I think that was just because environment, and you know how transporting these things and how picky they can get. The Grace Super chip and the Grace Hopper chip, they look very similar, but actually they're different connections, so you can't replace one from the other. And I won't go into it in this video because it's a longer video I want to do. But one of the companies actually had their Grace Super chip stolen at Supercomputing. Police were called.
I hadn't heard about that.
Police were called. Reports filed. It was there 4 p.m. one day, and when they went to pack up, they couldn't find it. So they're wondering who's taken that. But it's for a more serious video. I don't really want to get into it in a live stream. But yeah, good to see Grace and Grace Hopper on the show floor. I mean, we kind of saw them already at Computex.
Well, what's really exciting about Grace is it's the first chip that you can buy that has what's known as the scalable vector extensions for ARM, right? So for those like not super familiar, the idea here is that it's an Nvidia in-house CPU based on a core that they have licensed out from ARM Limited. And the idea here is that it's the first time that we're actually seeing the scalable vector extensions in a product you can buy. Currently, you have it from Fugaku and A64FX, which is a Fujitsu chip in a big supercomputer.
That's first version SVE.
Yeah, SVE1. And then you also had AWS's Graviton CPUs as a custom cloud offering that also offered SVE1.
Does Ampere's Ultra system not do SVE?
No.
Or Ampere 1. They're both on Neon / what's ARM calls Advanced SIMD, which are just not. It's why you'll see a lot of systems prior to Grace. You're talking about an ARM host, and then you're throwing a bunch of GPUs at it because you're actually doing the math on the GPUs. Because the CPUs, in a pinch, sure, but if you're deploying a center, they just weren't up to the task. Right. So what happens now is you can sort of think of SVE as almost like an AVX 512 in the x86 space with Intel and AMD. It's these extensions that are made to actually go and do lots of math very quickly on the CPU without needing a GPU. Right. And we're going to see those deployed in a lot of centers, namely the Jupyter supercomputer coming soon to to Jülich. Over in the EU is going to be the European Union's first exascale or exaflop system, meant for late to mid to late 2024 in terms of that being delivered, which is really exciting. And the idea is we finally have a chip that on the ARM side that you can buy and deploy at your university or your startup that can do real math, that can do real research, be it in machine learning or be it in more classical high-performance computing applications like, say, simulations or computational fluid dynamics. Really good on that sense. Really exciting to finally see it delivered.
So there is sort of one niggle in all this, And something that does end up that will actually apply potentially to Jupyter. The NVIDIA made a choice with their HPC compiler, and they're essentially only emitting 512-bit instructions. So any code compiled using the NVIDIA compiler for Grace is not portable to any other ARM CPU as far as I know. So that is going to be interesting for Jupyter because there's the Rhea partition, which is using it has Grace as Grace Hopper. So
it's two parts. It's Rhea CPUs and Grace Hopper accelerators.
Yes,
correct.
Yeah.
But when we say accelerator, we mean that the entire accelerated portion. They're not, say, Rhea CPUs from SciPearl with Grace Hopper attached to them. It's a fully different partition to the machine based on and around Grace Hopper. And that's where they're getting a lot of their compute for what that machine will eventually be delivered as. Rhea overall is based on an older design from ARM Limited, Neoverse V1 specifically. So it's a little bit, when that partition of the machine does arrive, it'll already have been a few years out of date. And the code that you're designing for one portion of it will not be portable to the other portion. So all the code that you're doing for Grace Hopper will not be portable across to, or the vast majority of your codes will not be portable across to the Rhea portion of the system designed and implemented by SciPearl.
So that's NVIDIA. H200, Grace Hopper. Now let's talk about something which wasn't technically at the show, but a lot of people were talking about it. And I'm going to leverage quite significantly here on Felix because he's actually done a lot of the legwork, because we're going to have an article about this coming up soon. But Microsoft, even though Microsoft Azure had the number 3 supercomputer in the top 500 in its new submission, and we've covered all that, they just happened to announce 2 new chips called the Maya 100 and the Cobalt 100. And ARM's really proud of this because they're based on ARM. And it follows the hyperscaler building own silicon to do its own thing. However, it turns out the HPC team didn't know much about it. And they were the only ones at Supercomputing. That's why they weren't invited to Microsoft's event. So
what was weird was being in the press room when this was announced, and you basically saw everyone wait, everyone be quiet, and let's go, and then you see everyone look at each other as if they can't quite know what's happened.
Yeah, basically.
So the big headline feature here is so there were 2 chips, one of which is for AI, the Maya 100 chip, and then one which is more general purpose CPU, which is Cobalt 100. So we'll start with Cobalt because we can sort of infer some things here. Microsoft has been very tight-lipped, both internally and externally, on what's going on with Cobalt 100. What we do know is that it's 128 cores, and that it's leveraging something that ARM calls ARM CSS, or compute system or compute subsystem, I believe.
It's basically a turnkey solution.
Exactly. So that way ARM can go and design most of the chip, and then various cloud vendors can go and integrate it into their platforms as needed. We've seen this play out previously with Alibaba's in-house ARM CPUs, which are basically using 2 ARM CSS N2, which is their general purpose cores, not their high performance cores, and sticking those together to make 128 cores. And that's what I believe is going on here.
It's a lot of people who like to use ARM's enterprise cores, the N's and the V's. Only as some of them take ARM's interconnect, because there are limitations there and they think they can do it better. And one of those is scalability. I know with the V1s, there was technically a limit of 72 or 68 cores. Or even 64, perhaps because that's power of 2. But lots of people design their own interconnect to be able to extend that to, like Ampere did with 80 cores and then 128. So
Ampere,
yeah, that's kind of what we saw with Graviton being limited into 64 cores if memory serves with Neoverse V1, and then also what we're sort of seeing with Nvidia, them doing their own interconnect to go chip to chip for Grace Super. But that chip itself it's hard to scoff at 72 cores, but at the same time, it's like, okay, could you have gone bigger?
It's one of the things in general is I'm hoping ARM does a deeper dive more into that. They do it for the consumer cores, their enterprise cores. I need a briefing on it. But sorry, Cobalt 100.
Yeah. So Cobalt 100. The idea, we're hard pressed for details, but what we do know is that it's based on CSS N2. So what that means is, hey, do we have 2 tiles, each of 64 cores, and then each of those tiles has 4 channels of memory? So 8 channels total, but there's also some, I'll call it loose speculation from some outlets that are claiming without much of a source that it's 12 channels of memory. And if they're doing that, the only kind of reasonable way of doing that is if they have 4 of 32 core tiles, and then on each of those tiles, they've disabled one of the 4 memory controllers to get to a better density. Because the idea with this chip is not super high performance. The idea is you have a lot of folks that are using cloud for, say, database workloads, for website hosting, and so on. And those workloads, they just don't need that much performance. What they need is they need I/O if they're loading up a lot of images, and they need memory capacity to store and load a lot of images at any given time. You're not going to be doing your AI applications on these systems, but you will be serving a lot of, say, web traffic.
Yeah,
if computational core is important.
You need to keep spinning up instances because your system keeps scaling, and that's what this is here for. It's almost, again, to bring up Ampere Ultra, it's kind of like that competitor or that comparison point.
Yeah, so what we're kind of seeing is that Ampere went out with their Ampere 1 system. And we're seeing, I believe that it's been confirmed that that's going to be coming to Oracle Cloud very soon. And we saw Google for their initial ARM offering, that was Ampere Ultra. We saw Microsoft, their current, up until Cobalt launch, their ARM offering is based on Ampere Ultra. So the only people that went and did their own thing up until now were Alibaba and were Amazon with their Graviton offerings. But now we're seeing that move in-house for their big 128 core, large core count.
For the investors that I help advise, that for the last 18 months, you can imagine the questions have been, what are the hyperscalers doing? Are they creating their own silicon? Do they actually have the people? And one of the things I keep saying is follow the people who make good chips, because that's who these people have been hiring. And well, we say good. This is the first kind of shock announcement from Microsoft to talk about their own silicon. So obviously more details. You pounded the floor and couldn't find any. Or the people who you tried to speak to had no idea because it's a different department of Microsoft. It's fingers crossed they're at Hot Chips. Yeah. Fingers crossed they're going to be at Hot Chips.
So then, oh, sorry. Go ahead, George. I feel like you wanted to.
So I was just going to say, so it does bring up questions. If Microsoft is spinning up their own silicon, what's going to happen to their current Ampere offerings, right?
They have customers who use those. As long as there is a business,
people stop using them.
Sure.
As long as there's a business reason to keep it, they will.
I was more thinking moving forward, what's going to happen? Because if you're spinning up your own silicon,
you're not going to be buying from someone else.
Guess who I'm interviewing in a couple of weeks?
Yeah. Renee from.
Yeah. So perhaps that could be a pointed question I ask her towards the end of the interview. So she doesn't kick me out first thing. So that's Cobalt. What's Maya?
So Maya's kind of interesting. We know pretty much nothing unless you're really into floating point specifications about Maya.
well, it has 4 HBM stacks.
Well, I'm just saying we've got the guy about floating point specifications here to talk about it. So
yeah, so we know three things about Maya. We know it's a big chip using 100 billion transistors, Microsoft talked about on stage. We know from the photos that it has 4 stacks of HBM, so probably 64 to 128 gigabytes or thereabouts in terms of total on package memory. of fast memory. And we know that it's using something called the MXFP floating point format, which was recently published. Which was recently published as part of an Open Compute project specification. So without going all the way into bits and bytes, what's going on is we've seen AI move to saying, we've seen the AI folks saying, hey, we don't need a ton of precision. So whereas high performance computing, classical high performance computing has a big need for FP32 and FP64, 64 bits and 32 bits per item that you're doing math on, we've seen that the AI folks can go and do, we only need 16 bits. And then they went, we only need 8. And then we need a little bit more than what 8-bit integers can give us, so we'll do it as a floating point format. And the idea here is you don't need as much data for each item. So what you can do is get more memory performance out of it, because if you can only move 128 bits at a time, you might as well move 16 8-bit things instead of 2 64-bit things if all you need is 8 bits. So what's happening now is this new specification is what's known as a block storage floating point. And the way to kind of think about it is, if we stay with those 128 bits, what happens is if you look at all those items inside of that you're trying to store there, you own almost all of them are within the same 1 or 2 orders of magnitude, high level. So what you can do is say, hey, almost like what video compression does, which is only store the main part and then only store the difference for everything, is that you can say for all of all these block entries in this sort of vector here, those are all going to have the same exponent minus 1 or 2 bits, and you can just do the difference. So it's a way to actually get more accuracy than, say, an 8-bit floating point, while actually using less bits. And then Microsoft has been pushing this as an idea since around 2020, when they came out with their initial proposal for what they called Microsoft floating point. And then that was how to get all the way to lower. Yeah, really good paper, good ideas. Some of it was a little bit, what are you doing? But we got there in the end with a reasonable specification that we're now seeing Microsoft use. And the idea here is that you get a lot more performance for the same amount of memory bandwidth that you have. And if you look at AI codes, it's the same reason that Nvidia went and upgraded the memory on H200 and got a huge performance increase, even though it's the same underlying silicon, is that a lot of these codes, they care about more memory and they care about fast memory, because we just can't feed the actual underlying silicon fast enough. So throwing more memory bandwidth or making what memory bandwidth we have more efficient is how you get to more performance at this point. And although for a lot of other applications, you won't be seeing this used, I don't expect to be doing, say, finite element analysis for if a bridge is going to collapse. Don't expect to be doing that with these block storage floating point formats. But if you're doing AI or things where you don't really need all that much precision, this is a reasonable performance and precision trade-off that you can use to get more out of it, which also brings and lowers your costs.
There's a video I want to do with Felix about quantization, and in the scrolling banner I've put, what is an FPA anyway? This is a topic that we've been discussing between me, Felix, and George for a little bit, and just because it's A, mind-numbing, B, stupid, but also really, really important.
Also, unsigned FP. Unsigned FP, guys, totally legitimate.
Yeah. So we'll get to that in a video. But we're an hour in, and I want to move things along. So Maya, Cobalt, new chips from Microsoft, done. So let's talk about a revival. And by this revival, I mean, let's talk about Omni-Path. And I'll title this section Omni-Path Lives, because it does, goddammit. Yeah. So for those of you who don't know, Omni-Path was Intel's attempt to create a high-performance computing interconnect. I was at the very first briefing at IDF 2015, Intel's developer forum, where they announced this stuff. I think they were talking about 25 or 50 gig NICs at the time, and then they came out with a 100 gig product. So this is networking. This is data center point to point. And then after that, they kind of mothballed the whole idea because they weren't seeing much traction. It's been in some supercomputers, really popular in Germany, apparently. And then it kind of died. And then it turns out that there was a company, not really a spin out from Intel, but from people from that team who decided to acquire the IP and the rights. And it took a few years, about 4 years, completely missed the 200 gig train. But they are now at Supercomputing 23 announcing a 400 gig product. Omni-Path. I'll preface this by saying Wendell has 11 systems with it and thinks it's really good. What are your guys' opinions on Omni-Path?
I think it's interesting. I think it could very much have a place. So I like that there are options. Options are good. And yes, Cornelis did join the Ultra Ethernet Consortium. So we'll see how that ends up going. I think
it's so the whole benefit of Omni-Path is one of the things in high performance computing is that you have to pass messages between nodes, and this is how we scale out in HPC. So this was built as a message passing engine. It could pass messages faster than everyone else, and as Alan says, the processors, Intel's own processors, fell behind the PCIe generation changes needed to drive. So of course, Intel's not going to put out a PCIe 4 or 5 product if they don't have a PCIe 4 or 5 CPU to go with it. But now Cornelis is so Cornelis, not Cornelius. Just to put that out there, they're completely detached from Intel now. That's why it took so long, and they missed the 200 gig train. I'm really excited just because it's fun having competing network technologies in the data center, whether that's machine learning, whether that's HPC. I mean, we've had InfiniBand forever. HPE does its slingshot stuff. We have Ethernet. We have Ultra Ethernet. I spoke to these guys, and they say they believe they can do 800 gig, so the next generation, on copper at a distance of 3 meters. Yeah, but the point is, you're saving by not buying $5,000 optical cables.
Well, yeah. Actually, so that's kind of what's exciting about Omni-Path is that even today, the kind of the top spec option, if you're maxing out everything and you have a sort of wish list right now, for most people at the top of their wish lists is InfiniBand, which was a Mellanox thing and is now pretty much completely owned by Nvidia. And it's great, not just because of the bandwidth, but because it has incredibly low latency and is very well optimized for what Ian was saying, for passing messages. The problem is, if you look at people who want to do InfiniBand in their HPC centers right now, there's 6 to 8 month lead times on getting in optics or cables or getting cards in right now. You just can't get it. So you have entire systems where they might have the computers, but they just can't network them right now. They're just sitting idle or sitting in their box waiting on optics to finally be delivered. And Lord have mercy on your center if you have a switch that dies and takes the optics with it. You're just screwed, right? To put it bluntly. So with that, what's interesting? Go ahead.
I just want to show people in this image. This is me with one of their I think it's a 576 port, big ass switch. And then this way, this is their new card. This is a mock-up of their new card for 400 gig. They're probing customers now, silicon next year, and then retail this time next year. So
one of the things I wanted to say is that I remember speaking to a company saying that when they were scaling out, like a good chunk of the cost was just the Ethernet cables. Like, I can't imagine how much that would skyrocket if you switched to optical.
That was me, because I was telling you a story about TensTorrent. They did a mock-up of their second gen chip, what it would look like if you made it into racks and racks and racks and connected it all together. Each chip had 16 connections. And I said, hang on, how much are the cables in that system? And I was told about half.
Yeah, I've been to far too many briefings if they cross over like that. But it does get insanely expensive. And even when copper is the cheap option. Like,
In quotes, cheap.
Well,
Yeah.
I mean, so you have passive copper and you have active copper, and companies like Credo, I think, do active copper connections. And then obviously the pivot is more to optical, but the price, it's especially when you're doing multi-wavelength, multi-frequency, high bandwidth cables, and not only within a data center, but data center to data center, you're talking about 3, 4, 5 digits per foot or per meter.
Well, so just to kind of as an audience thing, like to give you an idea, we're talking about interconnects at 400 gigabits per second. We're talking about interconnects at 800 gigabits per second. That means you do the math from bits to bytes, you're at 50 to 100 gigabytes per second. That's that one cable, that one connection is more bandwidth than the entire memory bandwidth of most consumer systems.
Yeah.
Right. Most consumer systems are coming in between, say, 40 to 60 gigabytes per second. That's one network connection, that is faster than the entirety of your system can move memory in and out of data. Right. And we're looking at supercomputers these days that will have 16 of these cards or connections on them just to shift data around your GPUs and your CPUs and your network IO and so on. Right. These are huge, huge amounts of data that we're trying to move. And then you're trying to do that over copper wire. Ugh,
Yeah.
It's a hard problem.
Even when they said up to 3 meters, that seems long for that speed. That's it.
Yeah.
3 meters seems like a significant length.
Well, you think you could bond 32 25 gig connections for better coherency, but then you got to buy 32 cables. And if anybody's tried to network 32 cables, and that's just one point-to-point connection, right?
I don't like managing my own home network. No, thank you.
Yeah. So let's move on. So one of the topics I wanted to cover, and perhaps we'll make this into a longer video, because it was very clear that supercomputing traditionally is a HPC show. All things about high performance computing. However, so much of the show floor was covered in AI accelerators, machine learning accelerators, silicon that makes bits go vroom vroom, basically. And there's a wider question about whether machine learning is HPC. And there are HPC supercomputers with AI systems attached. And whether they're doing machine learning or actual compute depends on the chip. I know, George, what was your feeling from the show? Did supercomputing feel like a HPC conference this year?
So, yes. So fundamentally, what HPC is making bits go faster. Fundamentally, so that you can get better, so you can get more data. And more data, not always, but as a general rule, is better data. Yeah, some people are going to yell at me for that one, but so it's always about making more data, more analysis. Great. But really what was actually interesting to me was more sort of moving back to, funnily enough, one of our original topics, MI300, and just paradigm shifts was sort of more the theme than anything, than HPC or AI. It was just, you're seeing paradigm shifts. So with MI300A, that's CPU and GPU on the same substrate talking to each other. Grace Hopper, same idea, just 2 different packages with a fast link between the 2. And then, of course, you had the AI companies who are hoping for a eventual paradigm shift towards them in some regards. And we're seeing some of that, but to a large degree, if you're doing stuff like a neutron in a gravity well, you're not going to be using FPGA. I can tell you that much. It's going to be FP64, or funny enough, a lot of folks use NEC hardware because it has in hardware FP128 scalar units. Hence why a lot of people still use power. So it really depends on what scale, like what spectrum you're on.
I mean, as people who watch this channel know, I've been dealing a lot more in AI hardware recently. And it's just crazy to see the amount of companies on the show floor that are from that world who thought this is a good conference to go to. And I mean, I get it. Some of these companies have systems that are attached to supercomputers and they've got a show face, but no, they're actively doing promotion. And I do want to go through some of these. And we won't really mention OpenAI and the whole crap that went on over there because
oh boy, that's
the story.
That happened after
mainly because it's already finished.
Yeah, basically, it's not over yet. So
it happened after the conference. So let's stick to conference. Now, I know Elad's probably going to be annoyed, but let's start with this company, Next Silicon. There's history with this picture. Let me see if I can bring up the next one. Okay. So Elad here is the CEO of Next Silicon, and I noticed he was wearing this t-shirt, with this design. And I went, that looks very familiar. That looks like Commodore 64. I've got my Commodore 64 t-shirt. I'll wear it tomorrow and let's take a photo. So he did. Then he tells me that his company headquarters in Israel actually have a bunch of old Commodores in the foyer as you enter the building. And Elad showed me a picture, and that was pretty fun. So interesting story for you. But Next Silicon, not necessarily an AI chip, but a software accelerator chip. So the idea is that you give it your code, it does, and you give it the parameter space, and then it finds what parameters give you the best performance by doing lots of running lots of little micro benchmarks with your code. It's designed to be hardware and software configurable hardware, which is really different to what everybody else is doing.
I actually find it really interesting. Personally, I think of all the silicon, like all the new startup companies, personally, this was the most interesting to me. Because it was just so different to what we normally see. And I actually really like the idea of sort of running micro benchmarks while you're running your code so that you can see what optimized best. Or
yes. So that's a question. What's the prelim it has to run before it runs your code? I mean, so I've zoomed in here and it says continuously reconfigure, optimize, and adapt to any HPC application. So it's done asynchronously.
Yeah, because so one of the things that's been this is more of the optimization background here. So one of the things that we've been doing for a long time is profiling code, and then this idea of profile guided optimization, where it's like, hey, you have this piece of hot code that, we have this fancy instruction that can work really well for it. But one of the problems you can do is by the time you set up your system to go and run that special instruction, you would have been better off because you're only there for a short amount of time just doing the dumber version and actually come out ahead in performance, right? So we've been looking at this as profile guided optimization for a long, long time. What's interesting here is doing things when you have hot code.
Sorry. That's a great tenor phrase. When you have hot code, you mean the performance limiting part of your code?
Exactly. Where you can have 10,000 lines of code, but if you're only spending if you're spending 95% of your time running 100 of those 10,000 lines, it doesn't make sense to spend engineering resources, engineering time optimizing the rest of it, because that's not where you're limited, right? You want to focus where you're actually spending time on that part of your algorithm. So what they're selling as an idea, as a concept, has been talked about kind of in the research space, in the chip design space for decades now, but they're the first ones who seem to have actually be doing it. One of the things that they were really tight-lipped in terms of what they wanted to share. Hopefully we'll see. I think they have an event coming up. Hopefully we'll see more soon. But one of the things we do know is that they have a big memory subsystem and the sort of unheralded star of the show, high bandwidth memory on board.
Yeah.
Because at the end of the day, if you can't get data to your computer resources fast enough, it doesn't matter how clever your chip is, right? So from kind of my understanding, they're looking at how can we set data up in memory so that it's always where we need it to be, and also how does it make sense to almost a little bit like an FPGA look at how your structure of your code maps to the underlying hardware. It's not, from what I understand, what they're doing is nothing like an FPGA, but it's the same sort of high-level concept of you can redefine how your chip is doing things because of what your code looks like at the lower level.
Yeah, they stress quite vehemently it's not an FPGA, but they have configurable cores. I mean, the product line, they've had first and second generation silicon, Maverick and Maverick 2. But a big part of their booth was wait until big things coming in 2024. So it's so the CEO, Elad, I showed a picture of him. I actually spoke to him for the first time a week before SC. And that they'd reached out like last year, and I just never got around to having that meeting with them. Their PR reached out and said, "Do you want to meet the CEO?" And I was kind of confused to what they did, and then we didn't end up having it. Then I actually reached out August, September time around Hot Chips, just because I kept hearing the name come up in various conversations. Somebody who we know in the HPC community used to work there, and we got to meet her for the first time. So I was grilling her about her thoughts about the company. And their name just keeps coming up. So I thought it was time to reach out, and Elad and I had a great chat. We scheduled like half an hour and ended up speaking for more than an hour and a half. So I'm hoping that when it comes time for them to do full announcements, we get some hardcore details, because it's an interesting chip and design. And also they're giving away big enter buttons that you bash that you attach via USB. Impractical but fun. Let's move on to another chip that was there. And this one, viewers of the channel, if you watch any of my AI hardware show episodes or podcasts with Sally Ward Fox and the EU Times, episode 6, I believe, episode 5 or episode 6, we covered New Reality. And they were actually on the show floor, NR1. And New Reality is again, it isn't an AI chip, but it's an AI optimizer. But instead of optimizing your code, it optimizes a lot of other stuff. So if you're doing video-based AI, it will have all the encoders and decoders that you need on the chip. It will help with database memory management and help accelerate I/O. What confused me when I did that recording is that they offered it as a PCIe card. Let's bring the PCIe card. It was episode 6. And you think that's an accelerator, right? You put that in next to a CPU and it does its job. No, that's the CPU. New Reality's chip is a CPU. It has some RISC-V cores in it, but it's a bunch of accelerators. And you essentially put it across a PCIe bus to your accelerator. And again, another company I didn't expect to be there. I actually first met them last year at IBM's AI forum, because they use IBM AI IP. I know you guys also spoke to them. What did you get out of that interaction?
So they were very insistent on not calling it a CPU. They're like, this system has no CPU. I'm like, it does, just you're being really cagey about it. But really, I think sort of the closest analog that people in this space would know of, it's basically a super DPU of sorts.
Yes. So
it has a CPU complex on it, but it also has all these other accelerators
and networking
for other things and networking. So it can just drop into a standard system if you want. But they're more marketing it as you put this in front of your AI chip, and this basically acts as your SoC to then control that AI chip for all intents and purposes.
I mean, one thing that amazed me at the booth is, firstly, despite the fact that they had a system with all these IBM accelerators in it, I've never seen these outside of IBM, and IBM have said they're only going to be available in clouds at IBM. So to actually see them on the show floor was interesting. But they also had a system, and let's see if I can bring it up here, with these bad boys. And I want to touch on this. Actually, we'll bring this conversation up. But Qualcomm's AI accelerator, if you've been following this space, you may recognize this. They announced it in 2020.
And they said very little about it after.
And then we heard nothing after it. And now we're seeing it here, Qualcomm Cloud AI 100. I mean, this is
what's weird about this, Karen.
I was going to say, this is a 75-watt accelerator. It does 400 TOPS of int 8. Were transformers a thing back early 21?
Early
really.
Research. We'd seen GPT-2 was out, GPT-3 was coming. So there'd been discussion about it. There'd been a lot of research papers, but we weren't seeing it anywhere near scale. But
most of the chips that came out when this was announced were CNN focused for convolutional networks for video processing. That's essentially the killer app for that. And because Transformers kind of took over, we didn't hear anything about it. Never heard of any deployments. Never heard of any work going on. Never heard of any libraries. And then in the space of Supercomputing Week, I heard about it 3 times. 1, here, New Reality. 2, Cirruscale is going to have a cloud-based offering with these available. 3, Cerebras actually mentioned it, that if you use Cerebras for training, they actually recommend this for inference. Weird. And 4, the AI 100 Ultra, which is the upgrade to this. I was like, well, hang on, we haven't heard much about this yet. So I'm pointing at my screen, even though it's covered up by name. But what, Qualcomm, where have you been? Also, for full disclosure, I'm a Qualcomm analyst. I'm they have a retainer with me. Mostly they talk to me about smartphone and PC. Qualcomm Orion. I've got an interview with the head CPU architect for Orion on the channel. That's worth a watch. And it's like, take me to your tech team. Take me to your AI team. Show me this. Talk to me about this. I want to know about this. This is important as well.
What makes this even weirder is, so I was editing the second batch of AI Hardware Show episodes, of which the Qualcomm AI 100 shows up. I was editing this about a week and a half before Supercomputing. So I was like, that's a weird card. We haven't heard anything about it. It was really hard to find B-roll and photos of. Go to the show floor. Wait, that's the... And then hours later, I got the email coming through saying AI 100 Ultra as announced. And I'm like...
Yeah. It doesn't make sense. But it was paired with New Reality, so they've got something going on with New Reality as well. How does that work out? What? Huh? It's if anybody from Qualcomm is watching, please tell me stuff.
Reach out.
Yeah.
I mean, I'm gonna speak to them after Thanksgiving anyway for a number of things. I also have a Snapdragon 8 Gen 3 review to do. All tested, all lovely spec benchmarks, but need to find time to actually record it.
And I have an 8 Gen 3 device coming that should be here tomorrow.
Ooh, which one?
The IQ 12. Well, a terrible name. One of BBK Group's many sub brands. But I have the IQ 12 and potentially 12 Pro. So if we need any real world examples, I can help with that.
So moving on. Sorry, go on, Felix.
No, I was just going to say that the sort of last thing about the AI 100 Ultra, their new kind of top of the line offering, is that they've sort of, you look at it and it's 150 watts, about 870 tops, which fine, int 8. but they've gotten the memory capacity right so that you can do things. Memory bandwidth is low at just over half a terabyte per second, but they do have 128 gigabytes on board, which for some large language models where you're capacity constrained, that could actually work out decently. So we'll have to see
if it does transformers, because George and I were talking about this just before the show. Is it 4x the SRAM as well?
Yes.
Yeah.
Massive
4x,
SRAM.
yeah.
Yeah, just over half a gigabyte of SRAM on board.
Yeah, so just over double performance for 4 times the SRAM, 4 times the DRAM, and 2x the power, because it's a 150 watt card, not a 75 watt card.
Yeah.
I would say that it's not 2x the performance, it's 2x the number of tops, which is a different metric. So
True.
It's potentially worse in power because they only ever called this a 75 watt class card. It just didn't need external power.
Yeah.
We'll see. Okay, so next company up is a company, if you've watched the channel a lot, I've spoken about a lot, Cerebras. This is their chip, the wafer scale.
Nice merch.
And because the CEO asked nicely, and Andrew, you owe me an interview and maybe a trip to Saudi to see your new system. But this is the only AI hardware company that technically has more in sales revenue than they have raised in VC funding. They just sold 576 systems for $1 billion to a Saudi conglomerate called G42. So CEO is spending a lot of time over there, and they're getting systems all sorted. I think they've stood up 1 of 9 systems. They're in the process of putting together the second. But big customer that's going to go well into next year and maybe even the year after to get all those systems up and running. This is a wafer scale engine 2. They've had it out for a while. I did ask about wafer scale engine 3, and they said, we'll talk to you when we're ready, and left it at that.
So something that's kind of interesting that, and I don't have an answer to this. This is more so for the call, is we've seen, as you were talking about earlier, Cerebras going, hey, go use Qualcomm's new AI product if you're going to be doing inference. But if you're doing training, do it all in Cerebras. Yet one of the problems we're running into with Cerebras is that, yeah, you have this massive wafer scale engine and it has a few gigabytes of onboard SRAM, but you can't fit anywhere near as a full model on that giant chip these days. So how are
80 gigabytes?
Yeah. Sorry?
80 gigabytes of SRAM on board.
Okay. Which that's an unfathomable amount of SRAM.
Yeah.
For us lowly humans. But simultaneously, when you're trying to scale out to trillion parameter models, what does that actually look like?
So I believe you also have DRAM that may be attached through a host, and the whole point of the software is to stream the data in. So they do put a heavy emphasis on cross-sectional bandwidth, and so you see this chip here. Actually, you can see my mouse on the stream. What they'll do is they'll partition the model such that you'll have one layer here, the next layer here, the next layer here, and it can stream the data into the right part of the model when it needs to happen. And the point is, you don't ever have to go backwards in your hardware to run another thread. It can just all be pushed forward, so you're all moving in one direction. Because obviously you got to think having power sustenance, having power over this thing is difficult. That's why it's got custom cooling and custom power integration, but also clocking. How do you clock a chip this big? It's not just simply done with retimers. You've got to manage that as well, because you're going to have additional losses in there. So that's part of what they've designed, and they seem to be getting good traction with it in machine learning. PSC, I think, has 2 systems now, and they're actually doing scientific compute, because this, as all the other AI computers that we talk about, massive matrix multiply, data flow, or CGRA, this is just a many core system. So you have 190
many cores.
850,000. But each core has 192 kilobytes of SRAM. So
not tons, but not insignificant either.
Well, I mean, that's equivalent of an L1 cache in an ARM core.
Yeah.
Right.
Yeah.
But it's literally half the physical size of the core is your SRAM. So this whole thing, it was TSMC 7 as well. So if they're moving to 5 or 3, then that adds in some benefits. Or if they're going stacked, or perhaps there's some optical in there.
So one of
that's. Oh, go ahead.
Sorry, Felix, Karen.
No, please.
One of the strange things I've been looking at Cerebras' products for years, like hot chips and everything like that, and you know how big it is. You can take measurements. You can print it out. You can do whatever you want. It's hard to get the sheer scale and the sheer density of this thing in numbers. Also, fun fact, if you get close enough, you can see the individual links between it. It's just so cool. And one of the favorite things about going to these events is it feels like being like a little kid in a candy shop, because there are so many just cool things and you just want to learn about them, and you do just end up staring at stuff. And one of the things I ended up staring at for a while was the WSE2 and the engine block they had next to it, which is another Cerebras product. But yeah, the weight of this thing, my God.
It's a chunky chip.
Yeah, it's a chunky boy.
So
Yeah.
the Tesla Dojo tile with the cooling block they have on it is 48 pounds.
What's that in real measurements?
22 kilos. Because they at Tesla's AI Day last year, they had guess the weight competition. If you win, you get a Cybertruck. No, you don't win anything. But
they'll send you a PDF with the model weights.
Yeah, how many microns you have to be out for the panels to fit, something like that.
Whoa. Hey! They're shipping end of this month.
I'll be the judge. I'll be the judge of that. Yeah, but Cerebras was there because they have deployments.
Mm-hmm.
So I put a SambaNova chip here. Yep. So next company is SambaNova. Again, another big AI company, over $1 billion in venture capital funding. Their big thing is the CGRA architecture, which is kind of like an FPGA. You have distinct compute and memory blocks, but they're partially configurable. Lots of. I met with a team there, and I describe you as the company that seems to be where the defense contracts go to in terms of AI hardware, because they have a number of them. They don't talk about them. They have a number of them. And the guy was like, well, we're trying to go beyond that. We can do more than just defense workloads. And so there's going to be, they are talking about some of their new customers. But here's me eating a chip. And here's the chip in full glory. This is their new SN40, technically called the SN40L. L for large language models. As you can see,
I wonder if that was a last-minute addition.
Yeah. Well, it clearly wasn't in the printing machine. Let's put it that way. So this kind of looks like MI300 or MI250X, at least anyway. What you have is, again, star of the show, HBMs. But what we have here is 2 compute die, one here, and then you can see just a line here and another one. Big chip using CoWoS, as you imagine. Again, the reason why they've had SN10, 20, and 30, which was the Cardinal family, and SN40 this, which is the Cerulean family. So there's a big architecture change here. They won't tell me what it is. I say, come on, Marshall, give us the goods, and he says, all in due time. So the nearest I got to it is, having a bite. But have you guys interacted with SambaNova in the past?
Not really.
Again,
they're not really on my radar. So
again,
they'll be in the radar.
Yeah,
but not on our radar.
Yeah.
Ayo.
The problem with like wanting to get away from defense contractor partners and not only be doing that stuff, it's that they pay really well. And if you
government money, baby.
Yeah. And it's guaranteed money too.
If they've got that cushy defense money, like, do they really want to risk it by because again, they're still relatively small. They only have a small product range. Do they really want to bisect there?
So that's
risk it for the biscuit.
That's a good point there. But
that was next Silicon T-shirt.
The problem,
it was actually,
with a lot of the defense work is that you're also locking yourself into very long support timelines, right? So you'll do 200 million in revenue, but you're also signing up to have to spend engineering resources and commitments to your foundry to respin that chip in 10, 15, 20 years time.
Or for 10 years. But one way around that is to build enough chips on day one for the lifetime of the contract, because that's what they did with titanium.
Yeah. And then never sold any more of them.
Yeah. But if one breaks down, you got to keep supporting that customer or pay a fine, or it depends on what the contract says. So and one of the kind of convenient things there, just briefly tangential, is that we're now seeing that modern FPGAs are fast enough and power dense enough and efficient enough that they're now just taking the RTL they wrote 15, 20, 25 years ago, running those on a modern FPGA and slotting that into the design, right? Yeah.
It's the only way to get foundry.
And FPGA news, Intel is spinning out its programmable solutions, the Altera group, for a partial IPO. We think only about 10%, kind of like the Mobileye model. They'll still have full, essentially, proper ownership. Yeah. But they won't be tied to any of Intel's processes and can do their own thing. That's going to happen. The company is essentially, the PSG group is going to be its own entity. That's happening in Q1. It'll be in the P&L sheet like Mobileye. It'll have a CEO, and then the IPO is going to be like another year or two ahead. So FPGAs are fun as well. One thing not in the list is that the number of tier 2 FPGA vendors at Supercomputing was surprising. If you ever want to go down that rabbit hole, it's a really interesting rabbit hole. I don't think there's enough audience interest in it. So I spend my time in things that I find super interesting. But if I had a clone, I'd get them to do that. So.
Yeah, like a last kind of touch point on the FPGAs, even though they're being spun out as PSG, is that it seems as though there's a want within now PSG, formerly Intel, formerly Altera, to continue supporting the FPGA stack through this open technology called SYCL, which is kind of an open source equivalent to CUDA. Come on, Altera.
No, Altera.
Yeah,
Altero. Very different. Very, very different.
So again, more AI chips. Let's breathe through this final section. TensorTorrent was on display, showing off their new Galaxy, which is their system where they're putting in, is it Grayscale wormhole chips into Galaxy? Wormhole. And it's basically a turnkey server design.
32 ones in a Galaxy for you.
Yeah. So it's not quite turnkey because for whatever, their design has power in the front or in the back, and it's 54 volt in. So it's
48 volt nominal.
Yeah, 48 volt nominal. It's a bit odd because it's not just a power connector, it's literally like ground leads, like terminal leads. So it's a bit strange. If I remember their booth correctly, they're having essentially a redesign with a big server OEM, starts with a Q. Can't remember.
Quanta, QCT.
Quanta, thank you. Yeah. QCT. So I suspect that will be the actual turnkey solution.
So most of their customers that they've announced, either AI, IP, or CPU, have mostly been in South Korea and Japan. So maybe built more for that market if the power requirements are different.
Maybe the other thing on the power thing is that the idea has been around for a while of why are we putting individual PSUs in every single device, right, to go from AC to DC. So what if we were to get one central power supply, say for the whole rack, say
better
at
efficiency,
rack scale cooling that we've seen? Exactly. So to drive down costs and lead better integration, especially when you're buying hundreds of racks at a time. Do you really want to be dealing with the cabling for IEC connectors? So
the problem when you're doing that is if you're now going from line voltage, so 220, 240 to 480, I don't know what most servers use, it's definitely not 110, down to 48 volts. The amperage required for those cables, the Galaxy server there is 7.5 kilowatts. That's a lot of amperage going through those cables. You're going to need significantly more copper per cable.
Yeah.
I could also pretend to be really smart here and list up all the specs. I do the tab in a different tab. So.
It's let's keep going because we're almost at 2 hours here, and I realize we're about halfway through the document. So Google had its I don't have a picture here. We've got it in video, but Google had its TPU V5e. Its new inference chip. They had a server board with 4 of those. Again, not talking much. The story I like to tell is one supercomputing. I think they had TPU V2 or V3, and I went up and I started asking lots of questions, and they started answering them. Then they said, "Well, who do you work for?" I flipped over my badge, and it said media, and they walked off. Yeah, that's how much they want to talk about it. I'm trying to learn more. Let's put it that way. But that was Google. One thing I want to touch on is the Korean chip vendors. So every time there's an event like this, you have countries that will sometimes send a delegation. Like you'll have the France chip ecosystem or the Germany chip ecosystem. Or very often there's a South Korea chip ecosystem. And they had 4 different AI chips from Korea, some of which... I think all of which I'd heard of 2 of them. I hadn't heard of 2 others. Let me see if I can bring up. Did I put any pictures here in our list? Let's see. We had Sapion, who are a multi-generation chip. Though I spoke to the guy and he couldn't really tell me much aside from the fact that it's data center inference. George, you had a better conversation, didn't you?
Yeah, so it's kind of similar to from what I gathered, it was a lot of just in terms of the architecture, a lot of just gem blobs, so matrix multiply blobs. They were let me look at my notes. They were comparing their newest gen to that's not the right way. There we go. The X330, they were comparing to
sound like the L4 T2.
Yeah, so they were comparing it to the L4 and the L40S, which is actually quite a large range there.
Yeah.
And their previous gen was A2 to A30, which again is quite a large range. They're spun off from the SK group. If you guys know SK Hynix. That's sort of.
No, I asked this. It's XK Telecom.
Yes, but it's sort of that family of SK, the SK group, right? If you in this space, SK Telecom is probably less known than SK Hynix for its memory. So the SK group,
So there was Sapion. Sapion were there with this chip. Furiosa what was there, but through another booth with their Warboy chip. I'm sure there's going to be some trademark infringement negotiations there, because their next chip is called Renegades. I'm hoping to hear about that soon. Another chip was Rebellions, another Korean chip called Rebellions. Good company name. Their first generation chip called Atom was designed for machine learning in financial markets, which is something that nobody else has targeted before. But again, they've pivoted to machine learning. And then we had MobileInt, a company I'd not heard of, that were doing, again, more sort of edge inferencey type stuff. I'm blasting through these now just because. But one company, they're not Korean, New Chips. Funny benchmark data they had going into the event. 700 tokens per second on Llama 2. 7 billion parameter. Grok, which we'll come to in a second, Grok is showing 300 on Llama 2, 70 billion. The thing is with this is their chip, but it's 4 of them on a PCIe card. We actually did this again on the AI hardware show. They actually knew who I was, and took a picture of me and posted it on their LinkedIn. That was fun. But yeah, standard PCIe card. Let's go to Grok, because Grok is amusing. George, explain what you saw in the morning.
The Grok Llama. Yes. They brought a Grok Llama, or a llama. Well, I think it was actually an alpaca, but
no, I confirmed it was a llama.
Oh, it was a llama. Okay. Then that was surprising, because it wasn't spinning. Because llamas are kind of mean. But yeah, so Grok brought a llama, and it was great fun because it was hilarious. I took that picture just walking from the hotel to the convention center was where I took that picture. And I was just like, wait, what?
Yeah, it's so my question is, where the hell do you rent a llama from?
Llamas are us. Duh.
Yeah, especially so it was there in the morning. It wasn't there in the afternoon. Yeah, and this is a llama. This is with the CEO of Grok, John Ross. His claim to fame is being an incredibly smart guy who designed the TPU. V1, V2. He was the head of that project. So he went to
the
Grok.
Google TPUs, you mean?
Yeah. I don't mean any others.
I don't know.
But their big thing is their chip is deterministic. So at compile time, you know how long your inference is going to run, and they are having a whale of a time with large language models. And the metric in large language models is what I said before: tokens per second. So a token isn't exactly a letter, but almost, and it's basically how many of those. And Felix has his llama on his. Meta's open source large language models are called Llama 2, so that's why everybody's playing around with Llama. And Grok said they could do 330 tokens per second. I don't think they made public on how many chips that requires or how much power, but I spoke to John and he said they haven't even touched the surface on how fast they can go. A lot of it is software optimization. A lot of it is in terms of networking, in terms of just making everything work together. But they're looking at orders of magnitude better performance for a whole system. So it's, yeah. Did any of you guys go by the Grok booth?
Me and George did.
Yeah.
So we got to see the actual Grok card itself, the LPU, the language processing unit, and we also saw, I think, 8 of them in a 4U rack with direct fiber cables connecting them together.
That was pretty.
It was a very pretty shade of blue. Reminds me of the old AMD Yinmin Blue. But yeah, it was so
just hanging your llama.
Yes. Yeah.
It's Felix now owns a meat factory.
Ooh. Ooh.
No, he's just hanging out. He's just hanging out, guys.
Yeah.
What was kind of fascinating about being at the Grok booth is how quickly I got pounced on for taking photos. I mean, I get it. It's what you agreed to when you have the media pass and everything like that. But what happened is I walked up, I was speaking to someone, they walked away, I started taking photos, and this other person came up very quickly and was like, who are you? Why are you taking photos? Are you sure you can take photos? And then they looked at my badge and said, I don't know who this is. And they got someone else over, and then they saw it said more than more, and they basically said, oh, he's with Ian, it's fine.
Yeah, it's I think I know who you're talking about. Grok, if anything, have a really nice marketing team.
Mm-hmm.
They're also really friendly. One of the things that last year, when I started the AI hardware show, I didn't really understand the architecture. I knew it was data flow, but the diagrams they were showing, and the way they were presenting the data flow seemed really weird. So I just said, "Can I have a chat? And can an engineer sit down?" Yeah, I could give their presentation word for word, but actually understanding it properly. And I just said, "I'm in the Bay Area. Does an engineer have time to have a chat?" And they said, "Yeah, sure, come out." And I think they agreed to Saturday at 8 a.m. And I was there for two and a bit hours. And the CEO even came in for most of that time. And we just had a long, deep chat about the AI space and how their architecture works. The Grok 1 is a little bit long in the tooth. This is what they've renamed to the LPU. And Sally and I keep asking about Grok 2. And again, we're being told we'll reach out when it's ready. I want it. I'm so used to CPU refreshes every 12 to 18 months that when a company takes 36, I'm like, oh, come on, guys.
Get your act together.
Yeah. And speaking of chips that have a long cycle time, let's talk about the first 2 nanometer chip. Which diagram should I go with? Let's go with this one. So
can I say something before you start with this?
Okay, go on.
You would not believe the speed at which Ian's head spun around when we walked past the Fujitsu booth and he saw this slide.
This is the first thing we saw on the first day, wasn't it?
Yeah,
literally the preview day.
Yeah, so we were walking past this to go see Tenstorrent, I think it was.
No, Supermicro.
No, I think we just left Supermicro.
No, we were still on the way because we were late.
Okay. But so yeah, Ian walked past, saw this and went bang, and was like, I need to speak to someone about this. And when the guy was off the phone, I was like, It was just like scanning the slide. It was magnificent.
It's my head stopped, but my body kept going, and my body had to calm, sort of Hanna-Barbera cartoon style.
Yeah.
It's so Fujitsu A64FX, a chip we know and love because it's high performance ARM, scalable vector extensions, a crown in CPU performance and memory bandwidth, HBM. So when somebody starts talking about the next generation processor from that team, we've got to stand up and take notice. That's why my head spun right around. And I photographed most of the slides, but this is the main 2. And the key point here, I think, if I can zoom in and show everyone, 2 nanometer. Ooh, we're finally talking about 2 nanometer chips. Has anybody else spoken about 2 nanometer chips yet? No.
I know Socionex talked about 3 nanometer.
Yeah,
but I don't think 2 nanometer has been talked about yet.
Yeah, so this is going to be an ARM v9 with Felix's favorite, Scalable Vector Extensions 2, for both AI and HPC. AI and HPC. I'll see it when I believe it. It's usually one or the other. And what they're talking about here is a system of 2 sockets, 144 cores in each, and 3D chiplets. And what they're doing here is they've got a core die on top of 2 nanometer and an SRAM die of 5 nanometer underneath, as opposed to AMD's Vcache, which does the additional SRAM on the top. The benefit here is the core die is the one that consumes all the power and gets hot. The nearer you have it to the top, the better you can cool it. Downside is it's furthest away from where the power has to come from. So you got to bring the power through, and that has issues with SRAM and the IO die. Moving from HBM to DDR5, PCIe 6. So this isn't coming anytime soon. Sort of 2025 at the earliest, 26 probably.
Yeah, so they've spoken about this being targeted for 2027 is when they expect this chip to arrive.
Yep.
Yeah, so in some ways it looks like a decent chip. It won't be an HPC chip. It won't be an AI chip. Will you be able to run those workloads?
Yeah,
right. It's a general purpose data center chip.
Yeah, that's what they were refocusing to, was more data center than towards HPC, and you can see that in their choice of DDR5 over HBM.
I was about to say, going from four channels of HBM to 12 channels of DDR5. That is
it's a haircut off the top for
because bandwidth wise, even going to 12 channels is still. So
it's not a lot. At this scale, it's not a lot. So, especially if you're trying to feed that many
and that's
cores.
HBM2 as well. We're on HBM3E. I mean, there's actually side note. I took a very beautiful shot of an HBM3 die at this, and Ian hasn't shown it yet, and I'm very upset.
So slight correction on what I actually said.
There we go.
Socionext actually did talk about N2. So it wasn't 3 nanometers, it was 2 nanometers. So a correction on that. But
so in terms of Fujitsu, Monica, apologies for pronunciation. Monaca. The claim there is that it'll support a few things that HPC and AI will be using. So you might be able to say you're doing a larger workload. You'll be able to do some local inference as part of that, say cloud or say website workload, but don't expect to be running large language models on this thing day in and day out. The big point here is that it's significant amounts of capacity based off of 12 channels of DDR5, and that you also have a significant amount of cores. Namely, you have 144 cores, which is a lot. The other kind of big ticket news here is that it's ARM v9 9.0 with SVE2, but it's also still a fully in-house core, right? So whereas we've seen a lot of the big vendors, so be it Graviton with AWS, be it Cobalt with Azure, be it Grace with Nvidia, those are all modifying, but still using the basis of the core that ARM Limited has been producing and then licensing out. This is Fujitsu still putting their foot down and saying, hey, we know what our customers want, and we can develop an in-house chip that is best suited for those targeted workloads. Also, by having the chip be ARM v9, but coming out in 2027, you can broadly assume that a lot of the teething issues around ARM v9 getting software support will all be in place in Linux and in core applications. So they'll be able to hit the ground running with software support for all of their features day one, which is precisely the opposite of what happened with A64FX, where it was the first chip, I think it was the first public chip anywhere to implement the scalable vector extensions as part of ARM. So they had to go and redevelop a lot of the compilers, a lot of the libraries, and so on to support these new extensions. So it's now they get to piggyback off other people's work.
So Joshua asks, how do you think Fujitsu will market this? Cloud providers? Who's going to pick this up?
I expect a lot of your tier 2 clouds are going to be looking at this or Ampere 1 or whatever the product is going to be from Ampere at that point.
Majority Japanese clouds will likely adopt this.
Because the benefit of having a homegrown design, they put a lot of.
Though I will say that there's some concern. I don't know if that's the right word. It isn't, but for what is 2027 product, only 144 cores. I know we were talking a lot about memory bandwidth starvation, but only 144 cores seems lacking.
So you see where it says 12 channels? Is that 12 channels across 2 sockets or per socket?
I bet you that's per socket. If that was cross socket, then that's only 6 channels, and that's
any is DOA.
Yeah,
also,
to exactly what Dom said here, you'd have to be.
Well, no, you have
it would be extremely strange to put it. Well, okay, so this is kind of a different conversation. But CXL does not solve your memory bandwidth problems. It doesn't. It can help your memory capacity problems.
Yes.
But one of the problems with CXL is that you're almost never going to be getting the same amount of bandwidth or the same memory characteristics as your built-in memories. Well, and then that's tiered memory, and that's a pain.
Well, so I did speak to SK Hynix on the show floor, and they actually have CXL memory attach, but computing memory attach.
Yes.
So that's another tier of memory. Maybe you have a pool of memory, which is just memory, and a pool of memory, which is compute memory.
So
they're all on the other side of the data set or connected over fabrics, and you cry.
So I saw a side from SK Hynix that was HBM PIM, LPDDR, and then CXL attached. So 3 tiers. And I can tell that Felix just wants to cry from that.
Yeah.
Well, it's we've seen tiered memory happen before, namely in the Intel Optane product, which for some applications,
Xeon Phi Optane CPU Max.
Yeah.
Same thing.
Exactly. We're seeing it still with CPU Max, where you have an HBM, and are you using that as cache or as a distinct tier of memory?
User manipulable, yeah.
Yeah, and there are workloads for which having tiers of memory is, especially if it's a lot of, say, fast local memory in the case of HBM, where that is a significant performance uplift, and you will do whatever you can to get there. At the same time, the increasing complexity means there's only a certain, say, class of customer that are going to be making the most out of these additional technologies, whereas for the vast majority of even cloud customers that will be using, or that will end up using CXL, even if they didn't want to be using CXL, they're just going to go and profile some of their applications on certain clouds, see that they got moved into the CXL partition of their memory, everything's way slower, and then they're going to look at, hey, why is my cloud performance so bad, right? CXL it's an interesting technology, but there's no free lunch with it. It helps alleviate certain problems, but it introduces a whole new class of issues, which is why you won't see everyone begging to please give me CXL attached to memory. If you have applications where you need, say, the extra memory capacity and you need to be able to expand to it, then sure, it's a great use case, but don't expect everyone to be jumping on board with that. And the same thing can be said for processing in memory, where not all workloads will take advantage of it because it's yet more complexity to deal with.
But if you can use it, there's a significant uplift. This is the mock-up. I don't think this is actually a usable design, but it's showing how it's using FPGAs with attached memory as well. Yeah, it's got nothing's populated. It's just a worker board. So do we want to cover? We don't have a slide for this, but China's supercomputer. I did at the top of the show talk about the top 500 systems that don't submit to the list, and China's a big part of that. But George, you've been doing some digging into what China actually has, the sort of Sunway systems.
Yeah. So we just released an article on the Sunway 26010 Pro chip and the supercomputer that they're using it in. I believe it's called Ocean Light.
Yep, that sounds right.
And, yeah. And allegedly exascale system. Whether it is or not, we don't know. However, in specifically this chip, we've been talking a lot about memory bandwidth and how that's a big thing in HPC. This chip has none of that. It relies on, so essentially you can think of it as 6 clusters in a trench coat, all acting as one chip, and each of the core groups, as you can see here, has its own DDR memory partition. However, this isn't DDR5. This is DDR4 3200, and this is only dual channel per core group. That's the same as what I'm running on my 5950X, and it has a 10th the rated compute or something like that of this chip.
Yep.
So memory starvation is, and not only that, it has tons of cache backing that fairly low memory bandwidth. This doesn't even have that. This is sort of an amalgamation of sort of cell-ish, if you remember the PS3, the cell processor, kind of like that, where you have essentially a scratch pad SRAM instead of like an actual cache. So it not only is it going to be hard to program, it's also going to be hard to utilize all that compute. But beyond just the chip itself, and Felix can cover more of this, but the networking, it's what's called 16:3 oversubscribed. Now, they have been able to get around this somewhat, but it's lots of optimization will need to happen. And that's sort of the theme with this supercomputer, is that lots of optimization are required and are needed.
So to be honest, I think this chip was built for a specific workloads in mind, because that's the only way you'd come up with this sort of architecture.
It's more like they had a chip. They needed to make a supercomputer hit exascale. So they just took their chip and scaled it up. And that's about it. Because there was the previous SW26010, which was 4 of those compute groups.
Yeah.
So essentially just a scale-up version.
I'm just imagining going to the fab with a little bin and just going like this. All of your all of them.
It's. I remember last supercomputing, these chips were part of the Gordon Bell prizes, right? So that must have been the regular, and this year they're talking about the Pro, but it's the same architecture.
Last year was also the Pro. These are fairly old chips. So these date from about Zen 2 era, so 2019, 2020, into 2021. So they're older chips, but I think really the big thing on these is just starvation. Not just of memory bandwidth, but of network I/O and network bandwidth. If Felix wants to talk more about that, he was.
I mean, to be honest, to give it some perspective here, 41 million cores, right? Compared to 8 million in Frontier, 2 million in Lumi, and you have undersubscribed memory
and network and storage.
But you're only hitting half of what Frontier is doing for how many more cores, right?
Yeah,
that's
sort of like
also what's relevant there is that as in their own numbers that they're publishing, they're calling out that they're having problems with efficiency at the FP16 mark, where you get to take your kind of double or 4x your bang for buck in your memory bandwidth, right? You look at that for, say, I don't know, particle physics applications, where this sort of system at a national scale would often be used. And then suddenly you're going to run into a lot of issues in getting data in. There's a second part to that, which is, well, you're still having to run all these CPUs while you're waiting for memory, while you're waiting for network, while you're waiting for storage. And I do not want to know how bad the power bill is. Right?
It's China. In order for them to compete on the world stage, they have to do stuff 10x in every dimension. Just not memory bandwidth or networking.
Yeah, and it's like
I won't go too far into this because again we're going well over 2 hours. George does have a great article on this over at chipsandcheese.com. I highly recommend that everybody checks it out, even though I showed a few of the images briefly here. And let's go on to our last couple of things, one of which I wanted to highlight here just because I found it utterly stupid. Let's see if I can bring it up. I'm a sucker for high capacity, but 30 terabytes in a hard drive. Come on. Gimme.
We saw 100 terabyte drives there, and you know it.
Yeah, no, okay, that's SSD based in a 3.5 inch. That's called the Extra Drive. Linus has done a video on it. I'm still waiting for my sample. But this is Spinning Rust, and Spinning Rust is sorry, I have to add this up. I asked John Ross of Grok because he's in the chat. Where do you go to rent a llama? And he says we have a guy.
Can your guy get in touch with our guys?
Yeah. The next question, John, is how much?
If you have to ask.
Yeah.
So yeah, this 30 terabyte drive. We've seen 20, 22, and I think 24 terabyte drives are in the market now. So to show off 30 terabytes, it's using their Hammer tech. $400 a day. Amazing. Ooh. But you have to be in Denver.
You know you want to.
You have to be in Denver. 30 terabytes Spinning Rust. It will probably cost an arm and a leg, but it's using heat-assisted magnetic recording. Really interesting to see this at Supercomputing. But then again, so many of the systems that we've spoken about today, they have hot storage, they have flash, but they also have lots and lots of cold storage. If you go back 4 years to when they did, the person doing the keynote was their main person, or the person in the team who did the black hole as an image discovery. If you look at how much data they had on hard drives due to all their telemetry data, their astrophysics data, that was petabytes and petabytes of hard drives because that's the cheap effective option. But yeah, so we saw a 30 terabyte drive on display, and they showed it transparently.
Is this one of the dual arm ones, or is this still single arm?
This is still single actuator. Dual actuator, obviously, you end up hitting more of the SATA limits in performance. I'm pretty sure this is 10 platters at 3 terabytes a platter. The only thing I asked the people at the booth was to turn the noise down so we could actually record a video. So we're going to go edit those up because it's really fun, and I like high density storage. But to wrap up here, one last question I want to ask these guys, because for me this was my 4th or 5th supercomputing. For the other 3, it was their first. So, and George, I know you've been to Computex. Dom's been to a number of other events. He also reviews some smartphones and 3D printers. Felix, this was your first ever tech event, and you have your I am HPC Guru badge. Felix is not HPC Guru, just for clarification.
Are we sure about that?
I'm HPC Guru. No, I'm HPC Guru.
We're all HPC Guru.
Yeah.
Oh, I disagree on that front. I'm not.
Well, so that was kind of the theme of the show this year was I am HPC, and then obviously some of us ran with the joke of I am HPC Guru because of course, and I think that speaks to what HPC sort of is, right? Not to get too philosophical and too lovey-dovey with it, but a lot of what happens in and around HPC beyond cool hardware things and cool software things is the people that are enabling the work and the science to be done, enabling the research. And at the end of the day, this is all about bringing people together to look at the new tools and ways to advance that for our users with that. And to kind of touch on points that we touched on previously in the show and over the course of the live stream, there's a question of like, is AI part of HPC, right? And I'm fall into the camp that HPC is the resources, and then we have classical HPC workloads, which is a lot of your scientific computation, your engineering applications. And then now we have a new emergent workload that needs HPC resources, right? Lots of compute, lots of networking, lots of storage, right? And with that, and that's one of the things that made it interesting to see all the AI vendors that are all targeting their chips, that at the end of the day, if you look at them, they're just trying to solve a how do I scale problem, right? And scale is what HPC has been doing for decades. So in terms of first time at the show, amazing being there, exhausting, lots of coffee needed.
Hey,
right? It's
you went to the parties. You're young enough.
I did go to the parties.
Well, so did you, Ian.
I went to some of the parties.
I went to one.
Some of them.
I would like it to be noted that I am an old bastard who didn't go to any of the parties.
No, but a lot of that was like, let's talk to people, let's share all of these great ideas. And there's a very welcoming atmosphere of people. There are people there that have been coming for 35 years, and there are people there for 5 years, 10 years, 15 years, and so on. And then you have total newbies who are relatively new in the industry, like yours truly.
Or students.
And there's a big community.
Plenty of students about.
Loads.
Yes. So many students.
Yeah, so many students.
I mean, and not to butt in here, but it's part of that gives the Supercomputing as an individual show its innocence. But it's more than that. It's the camaraderie. Everybody's there to benefit humanity and not to... I mean, okay, yeah, there are people who don't like each other and there are people who butt heads. But again, it's a philosophical difference. And I think everybody underlying agrees we're all here to help each other.
Yeah.
And whereas a trade show like a CES or a Computex is more about how many meetings can you fit in a day. This is why I love research events, because everybody's there not for personal gain, it's for collective gain.
Yeah, and that's shown off like even on the passes, right? You have media passes, but one of the things that Supercomputing is big about is making sure, hey, if you're media, you still have access to all the tutorials, all the research sessions, all the birds of feather events, right? Because the trade show floor is cool and everyone's exhausted if you're on the floor. But a lot of what makes supercomputing is the research, is the people, and making sure that that research gets talked about. How are we advancing the state of the art? And also, how are we making sure that the people that can't go and install the new state of the art chips are finding new ways to get the most out of their hardware, driving efficiency gains, driving usability upgrades, right? Making sure that a grad student doesn't have to go, whose background is chemistry, doesn't have to go and become an expert assembly programmer. How do we make the tooling easier, right? To make sure that that's available to everyone. And that sense of camaraderie, that sense of helping, that sense of openness in everything we do, it was amazing.
Science gets done and people are still alive.
Yeah, exactly. I mean, some of the attendees are still recovering from catching COVID. But it's these sorts of events where if you're struggling with a problem for 5 months, you go to this event and people ask you about what you're doing and you'll riff off, and it's just 1,000 people to bounce ideas off of as well. And maybe somebody will suggest this, somebody will suggest that, and you end up coming back with so many things you want to think about and talk about. The difference here, I think, for me, perhaps different to you, Felix, given it was your first time, is I go to so many events. I fall out of one into another. I mean, I've got another 3 in the next 2 weeks, and then comes CES. For some people at this show, it's their one and only major event of the year. So they're planning for weeks in advance. I'm going to go to these talks at this time. I'm going to meet up with this people at this time. So much organization goes into it that they get so much out of the event. And to be honest, I'm usually surprised at just how in-depth supercomputing the planning has to be for such a short event. Because, I mean, it's 4 days? Or if you include the tutorials and the extended, it's more like 6. But there's just so many things to see and do. You can't honestly have enough time for how long the event is to do everything.
Also, shout out to the SciNet folks.
Yeah.
Oh my gosh, yes.
Yeah, for their job is just, I don't even want to think about the logistics of that.
Yeah. Well, they're already planning. SciNet's deployment for 25 is already happening.
So
for 25.
Explain what SciNet is.
So SciNet is the kind of short-term event network, if you will, right? They make sure that every attendee has Wi-Fi, but they also make sure that all the people doing booths, doing tutorials, showing off science have a connection back home to be able to run off of massive data sets. for a 1 week event, 4 days on the floor, they have a multi-terabit per second interface to the broader internet. Right?
6.7 terabits.
6.7 terabits per second, and that's connecting all the way to Japan and South Korea. That's all the way to CERN in Europe. It's across North America, all the way down to South America as well this year.
So there are two things. One, there's a reason why they only hold supercomputing at certain venues, and it's because they have access to all this sort of stuff. And two, if any SciNet people are watching, people who need networking are in the media center. Unfortunately, as in physical networking, if we're recording videos and you're dealing with 10, 20 gigs at a time, we need that connection too. Thankfully, somebody did sort it and we did get it done and it was amazing. I will say, though, that
it wasn't fun downloading 175 gigs over Wi-Fi.
No.
It was magnificent, but they got it fixed and it was so...
Well, once we plugged in and got gigabit, fine. But I will say the emergence of machine learning as a workload at supercomputing has meant that some of these data sets are that remote and they do have to bring them in just to run it dynamically. I never get a chance to just sit and look at some of the stat screens that they put out at SciNet. But to be honest, that's an infrastructure marvel in of itself. Unfortunately, the only people really interested in it are deep infrastructure nerds. But it's something that needs to get done.
I mean, these two actually went on like a tour of SciNet.
Yeah, a cool thing this year where they actually brought some of the media folks that were in the room behind the scenes of SciNet to show not only the big cool racks with terabits of infrastructure, but also like, here's the command center for doing Wi-Fi. Here's the command center for sysadmin. Here's the cybersecurity like teams, like multiple teams that are in shifts because they show up.
Like 200 people literally in the middle of the floor that you don't see anything of for all intents and purposes. And they're basically the ones keeping the show running. And without them, there would be no show for all intents and purposes.
I mean, if anyone has been to a trade show, you've known what an RF nightmare it is. Like, we had issues with our microphones and stuff like that, but not just because a lot of people have microphones, just because of the sheer amount of devices and Wi-Fi and everything like that. For them to make an event with this many people, I think it was 16,500 attendees.
14,500
attendees, and the sheer size of the trade show floor, having any sort of usable network, and a reliable usable network, is no small feat.
No,
and you cannot praise these people enough.
Yeah, and it's like one of the things they talked about as a sort of example to that is you'll have people walking over the same parts of the carpet all day long, right? And they have fiber runs underneath them. So they have literal teams ready for when that fiber breaks because too many people have just been walking over it, or someone lifted something heavy and dropped a server and it cut the line. They have literal teams on standby to go through and repatch and reconnect and remelt those fiber drops live. Yeah. And then in the meantime, they will route to redundant links around the rest of the show floor just to get around that drop in that fiber. Frankly, it's amazing.
George, you went to more of the talks than anyone else, I think. How was that for first time going to a research conference that wasn't called Hot Chips?
So the talks were very, very good and very, very interesting. Like that's where some of the photos for the Sunway system came from, where some of the talks being held. And it's the show floor is like was said, the show floor is great, but it's really those sort of tutorials, the birds on the feather, and all this that really makes supercomputing and not just, hey, here's an exhibition of all the different vendors of stuff. So,
well, I mean, compare it to Computex that you did earlier in the year, a trade show, not a research trade show.
Yeah, no, in terms of the two, Supercomputer was smaller, surprisingly enough. I know how crazy that sounds.
By a factor 10, yes.
Yeah. So it was much less crazy. and was more laid back. And I really did appreciate that sort of more laid back and how you could literally just stop and talk with somebody for like 2-3 hours.
That happened more often than not. I mean, it to be honest, also given the industry it's in, it is a room full of introverts as well.
Yeah.
Aside from the one or two marketing people who you tell to buzz off, if they get a bit too aggressive. I mean, I'm getting emails from people saying, "Do you want to rewire your network infrastructure?" Just because I'm signed up to the Supercomputing press list.
No, he wants to rewire his house for anything better than 80/20.
Yeah. Yeah, that's the comment I made. My home internet is worse than what I had at university 20 years ago. And the fact that I have to say at university 20 years ago makes me sound really sodding old.
Sound?
Well,
and that's how you get your media path revoked, Felix.
I went to the show.
You don't get to talk back until your third event.
Sorry, how old were you 20 years ago? Oh.
Do you actually want the answer to that?
Yeah, I know the answer. I'm just
exactly.
No. The turning point for age is when you start interviewing CEOs younger than you. Yeah, that's the face. That is the face. That's the face. That happened to me last year. Dear God.
I did meet a multimillionaire at this event who was younger than me, and that was depressing enough.
Well, George works for him. Sorry. Inside joke. So supercomputing as a whole, if you get a chance, will you be back next year?
Yes.
Unquestionably.
Yeah.
And what would you say to people who are thinking of going, but can't get there? So Felix, knowing what you know now, if I hadn't paid for you to go, would you still pay your own money to go?
Yeah, I wasn't in a position to, which is why I'm so incredibly thankful for having gotten the opportunity to go. And I've heard people talking about SC as like, this is where this becomes the mecca of supercomputing for about a week, right? And to kind of make that more accessible, Supercomputing has done a lot of work for their digital experience, making sure every session is live streamed and so on. And making sure it's about the people and it's about the research. But supercomputing lived up to and exceeded the amount of hype that's been discussed around it many times over for me. There are more. I could have been cloned 3 times over and still not gotten everything out of that show, right? There is so much to talk about. There's so much amazing research, amazing hardware, amazing software being worked on and discussed, and these ideas that are just thrown out of left field. It's like, oh, that's a great idea, right? Let's go and do a talk on that for next year. Let's go. We've been doing this amazing thing in our small university cluster, and now that's applicable to the top systems in the world. And this is moving the state of the art forward out of these incredibly small teams. And back to the people aspect, there's a willingness to share and a want to share of like, yo, guys and gals, I'm doing this a really niche but really cool thing. You should come look at it. And there's this energy that's pervasive everywhere of like all these amazing people, these that are everywhere from pre-undergrad high school students visiting the floor to people that have graduated and been leading teams of postdocs for decades. And everyone comes with that same like giddy, borderline childlike smile of just like, let's just go and do something amazing. And let's share it all. And it's pervasive. It's amazing. It's just amazing.
The sheer amount of genuinely just cool shit was so fun. It doesn't matter if it's like the beginning of a $100 cluster or multi-million-dollar fiber connected. Like everyone was so excited to show off their stuff. Like one of my jobs on one of the days was going around taking B-roll of interesting things. And Felix said if he had 3 of himself, he would have missed stuff. I would have missed stuff. And I was literally just walking the show floor.
We spent half a day doing like little short recordings. I haven't decided whether those videos are going to be 3.5 minutes by themselves or I'm going to put like 5 of them together and do a collective. But yeah, I felt like by the end of the day, we were running out of time, not content,
100%.
time.
Yeah, every time.
So, well, so we've gone past the 2.5 hour mark, guys. Any final comments about supercomputing?
Go if you can.
Yeah.
Go if you can.
Next
year.
Yeah, and if you're going, reach out. If there's enough interest, we'll do a chips and potato meetup.
Chips and dip.
No,
And if and when it's ever in Canada, I'll make you guys some homemade poutine.
Oh dear God, no!
Ooh.
I gotta try it at least once.
Make you guys the real stuff, the real homemade stuff,
Ooh.
not the crap you get at the airport.
You mean the stuff I get from Tim Hortons isn't real? Come on.
So,
See, that's how you know he's a real Canadian. He's pissed off with Timmy's.
Timmy's changed hands 10 years ago.
Yeah.
I was going to say the
So-
Burger King buyout, but even then,
Yeah.
it started before that when they stopped doing everything fresh in house in the morning. It used to smell the donuts from like a kilometer away.
All right, I feel like this could end up going for another 2.5 hours if I get him on this tangent.
easily.
So
Sorry, go on, George.
no, I was just going to say, so Nicholas in the chat, this versus Hot Chips, two very different things.
Oh, entirely.
Two very different shows. One is very much, you have 2 days of just sitting and getting presentations and just absorbing all that knowledge. Supercomputing is 4 to 6 days of walking around, talking with people, and absorbing knowledge that way. It's two very different things. I enjoy them both. I love them both. And I wouldn't compare them to each other. They're just so different.
Hot Chips feels like you're back in university.
Yeah.
This feels like you're at a job. And again, I've covered multiple trade shows before, like IFA, NWC. Those are orders of magnitude larger than this, multiple buildings, multiple floors. But it's been my first trade show since COVID. And you forget. You forget just how much walking. So if you buy new shoes, break them in beforehand. So many.
Yep.
Yeah. Guess who didn't do that?
Yeah, guess who didn't. But yeah, no. This, if you can make your way to a supercomputing event, even if it's just try and do it. It really is that. It is that different of an event.
It's international supercomputing is a little different because it's a quarter of the size. But perhaps we'll get some big things with El Capitan next time around. So with that, I'm going to end the live stream here. Can I ask you guys to stay on just to make sure this all wraps up fine? But everybody else in the chat, thank you for coming along. We have had a ton of viewers come in throughout the 2.5 hours, and familiar faces in the chat and new faces as well. Thank you for stopping by. And if you like what you saw, like, subscribe, go see George's stuff on Chips and Cheese. Felix has got some stuff there. And hope to see you for the other videos that are going to drop soon. So yeah, take care, everybody, and thanks.
Happy Thanksgiving for those who celebrate.
Have a good one.
Thanksgiving.
Yeah, and happy Thanksgiving to all my fellow Americans.
Happy Thursday.
Cranberry sauce belongs in a can.
No.